Imagine a cosmic tug-of-war. On one side, gravity, the universal force of attraction, relentlessly pulling everything together. For decades, centuries even, we believed gravity was winning, slowly but surely slowing down the expansion of the universe that began with the Big Bang. It was a comforting, predictable picture, a universe destined, perhaps, to eventually collapse back in on itself in a big crunch. But what if everything we thought we knew was wrong? What if instead of slowing down, the universe is actually speeding up its expansion? This isn't science fiction. This is the monumental discovery that rocked the foundations of cosmology in the late 20th century. It was like discovering that an apple, instead of falling to the ground, suddenly shot upwards into the sky. A complete rewriting of the rules. For years, scientists operated under the assumption that the expansion of the universe set into motion billions of years ago was gradually decelerating. Think of it like a car rolling uphill. It might start with momentum, but eventually gravity, in this case the combined gravitational pull of all the matter in the cosmos, would slow it down. It was a logical, intuitive model. After all, what force could possibly overcome the relentless pull of gravity on such a vast scale? The implications of this accelerated expansion are staggering. It suggests that there is a mysterious, invisible force at play, a force counteracting gravity, pushing the universe apart at an ever-increasing rate. We call this force dark energy, a name that acknowledges our profound ignorance of what it actually is. It's like discovering a hidden puppeteer controlling the cosmos from behind the scenes. This repulsive force, this dark energy, is not some minor correction to our models. It is estimated to make up nearly 70% of the total energy density of the universe. 70%. That means everything we can see, everything we understand, all the stars, galaxies, planets, and even us, represent only a tiny fraction of what's really out there. We are, in essence, standing on the tip of an iceberg, oblivious to the immense, dark ocean beneath. This discovery isn't just about numbers and equations. It's about our place in the cosmos. It's about the ultimate destiny of the universe. If this acceleration continues, and all indications suggest that it will, the universe will become increasingly vast and empty. Galaxies will drift further and further apart, eventually disappearing beyond our observable horizon. The night sky, once filled with the light of countless stars, will slowly fade into an infinite, lonely darkness. Understanding this accelerated expansion is not just a scientific curiosity. It is the key to understanding our cosmic future. It is a puzzle that demands to be solved. What is this mysterious dark energy? Where does it come from? And what does it mean for the fate of the universe and everything within it? The answers to these questions lie at the heart of modern cosmology, and they are driving some of the most ambitious scientific endeavors of our time. So, we are left with a tantalizing question. If gravity isn't the dominant force slowing the universe's expansion, then what is this mysterious something pushing it apart? Scientists, confronted with this cosmic conundrum, did what scientists do best. They gave it a name: dark energy. A name that is as fitting as it is frustrating. Dark, because we can't see it, we can't directly interact with it, and we have little to no idea what it actually is. It is the ultimate cosmic ghost, influencing the universe on a scale that is almost incomprehensible. Think about that for a moment. We are surrounded by this unknown force. It permeates everything. We are swimming in an ocean of dark energy, yet we can't touch it, taste it, or even detect it directly. It's like trying to understand the wind by only observing the trees swaying. We see the effect, but the cause remains elusive. Imagine trying to solve a crime with only the faintest of footprints left at the scene. The clues are there, but they are incredibly difficult to decipher, and the numbers are truly mind-boggling. Current estimates suggest that dark energy makes up nearly 70% of the total energy density of the universe. That means everything we can see, All the stars, galaxies, gas clouds, and even the tiny amount of dark matter we've managed to detect constitutes only around 30% of the universe's total contents. We are only seeing a small fraction of the total picture. It is a humbling and slightly terrifying realization. But what exactly is this dark energy? Is it a new type of particle we haven't yet discovered? Is it a fundamental property of space itself? Or is it perhaps something even more exotic, something that defies our current understanding of physics? These are the questions that are driving the next generation of cosmological research. These are the questions that are pushing scientists to the very limits of human knowledge. The truth is, we simply don't know. Dark energy remains one of the biggest mysteries in modern science. It's a cosmic riddle that has stumped some of the brightest minds on the planet. It's a problem that requires not just meticulous observation and sophisticated analysis, but also a healthy dose of imagination and perhaps a little bit of luck. Some scientists theorize that dark energy might be related to something called vacuum energy, the energy inherent in empty space itself. Others suggest it could be a new type of dynamic energy field, constantly evolving and changing over cosmic time. And still others are even questioning whether our understanding of gravity itself is complete, suggesting that perhaps dark energy is not a thing at all, but rather a manifestation of gravity behaving differently on the largest scales. It's a 360-degree view into the greatest mystery of our time. Whatever the answer may be, one thing is certain. The quest to understand dark energy is one of the most important scientific endeavors of our time. It is a quest that could rewrite our understanding of the universe and our place within it. It is a quest that could reveal the ultimate fate of the cosmos, and it is a quest that is just beginning. The universe is expanding, but what will be next? So, we are left with a tantalizing question. If gravity isn't the dominant force slowing the universe's expansion, then what is this mysterious something pushing it apart? Scientists, confronted with this cosmic conundrum, did what scientists do best. They gave it a name. Dark energy. A name that is as fitting as it is frustrating. Dark, because we can't see it. We can't directly interact with it, and we have little to no idea what it actually is. It is the ultimate cosmic ghost, influencing the universe on a scale that is almost incomprehensible. But the story doesn't end there. In fact, it takes a rather ironic turn, a twist worthy of a great scientific drama. To understand this, we need to journey back to the early 20th century and meet one of the greatest minds in human history, Albert Einstein. Now, most people know Einstein for his theory of relativity, the famous equation E equals mc squared, and perhaps that wild hair. But what many don't realize is that Einstein played a crucial role, albeit unintentionally, in the story of dark energy. Imagine Einstein, in the early 1900s, grappling with the implications of his own groundbreaking theory of general relativity. His equations predicted a universe that was either expanding or contracting. But at the time, the prevailing view was that the universe was static, unchanging, eternal. It was a view deeply ingrained in the scientific psyche, a cosmic status quo. Einstein, a man who dared to challenge conventional wisdom in so many ways, found himself constrained by this prevailing view. He believed, along with most of his contemporaries, that the universe must be static, but his equations stubbornly disagreed. So what did he do? He did something that he would later call the biggest blunder of his scientific career. He introduced a fudge factor into his equations, a mathematical fix to force the universe to be static. He called it the cosmological constant. Think of it as adding a counterweight to a scale, a force that perfectly balanced gravity, preventing the universe from collapsing under its own weight. It was an elegant solution, or so it seemed at the time. Einstein had saved the static universe, at least on paper. But the universe, as it often does, had a different idea. Enter Edwin Hubble, an American astronomer who, in the 1920s, made a monumental discovery. Through meticulous observations of distant galaxies, Hubble found that they were moving away from us, and that the farther away they were, the faster they were receding. The universe, it turned out, was not static at all. It was expanding. Einstein, upon hearing Hubble's evidence, was reportedly crestfallen. His cosmological constant, the mathematical trick he had devised to save the static universe, was no longer needed. He famously declared it his biggest blunder. A scientific misstep that haunted him for years. But here's where the irony kicks in, the twist in the tale that makes this story so compelling. Decades later, when scientists discovered that the universe's expansion was not just continuing but accelerating, they were faced with a profound question. What was causing this acceleration? What was this mysterious dark energy that seemed to be pushing the cosmos apart? And then, someone had a rather audacious idea. What if Einstein's discarded cosmological constant, his biggest blunder, wasn't a blunder after all? What if it actually represented a real force, a repulsive energy inherent in space itself, driving the accelerated expansion of the universe? It was a revolutionary suggestion, a complete reversal of fortune for Einstein's maligned constant. Suddenly, his blunder became a leading candidate for explaining the most mysterious force in the universe. Perhaps Einstein was right after all, just for the wrong reasons. He was trying to create a static universe, but his cosmological constant, if it exists, is actually creating an accelerating one. The cosmological constant, in this new light, represents the energy density of empty space itself, a kind of background energy that permeates the entire universe. It's a simple explanation, elegant in its simplicity, but also deeply problematic. You see, when scientists try to calculate the value of this vacuum energy using quantum mechanics, they come up with a number that is vastly, and I mean vastly, larger than what we observe. In fact, it's off by a factor of something like 1 followed by 120 zeros. It's a discrepancy that has been called the worst theoretical prediction in the history of physics. So, is Einstein's cosmological constant the answer to the dark energy puzzle? It's a possibility, and it fits the observational data reasonably well. But the theoretical challenges are immense. It leaves us with a profound question. How can empty space have energy? And why is that energy so incredibly small, yet still powerful enough to drive the expansion of the entire universe? The universe is accelerating, but maybe there is another answer? But even with Einstein's cosmological constant potentially back in the game, there's no denying that the early 20th century was a time of profound paradigm shifts in our understanding of the cosmos. Imagine a world where the Milky Way, our own galaxy, was believed to be the entirety of the universe. It was a cosmic island floating in an infinite dark void. Then, in the 1920s, a game-changing discovery shattered this cozy picture, forever altering our perception of the universe. Enter Edwin Hubble, a name that deserves to be etched in the annals of astronomical history. Hubble, working at the Mount Wilson Observatory in California, was meticulously observing faint, fuzzy patches of light in the night sky. These nebulae, as they were called, were thought to be clouds of gas and dust within our own galaxy. But Hubble, with his keen eye and access to the most powerful telescope of the time, the 100-inch Hooker telescope, was about to rewrite the cosmic rulebook. Hubble's groundbreaking work focused on measuring the distances to these nebulae. He used a clever technique involving Cepheid variable stars, stars whose brightness fluctuates in a predictable way. By measuring the period of their pulsations, Hubble could determine their intrinsic luminosity, their actual brightness. Then, by comparing this intrinsic brightness to their apparent brightness, how bright they appeared from Earth, he could calculate their distance. It's a bit like knowing how bright a light bulb is supposed to be, and then judging how far away it is based on how dim it looks. What Hubble found was astonishing. These nebulae were not located within our own galaxy. They were vastly more distant, far beyond the confines of the Milky Way. They were, in fact, entire galaxies in their own right, island universes scattered across the vast cosmic ocean. Andromeda, the great nebula in Andromeda, was revealed to be another galaxy, a sister city to our own Milky Way, located millions of light years away. It was a mind-blowing realization. Our galaxy was not alone. The universe was far bigger, far more expansive than anyone had previously imagined. Think of it like discovering that your small town is actually part of a vast continent, teeming with other cities and civilizations. But Hubble's discoveries didn't stop there. He went on to make an even more profound observation, one that would lay the foundation for modern cosmology. He noticed a relationship between the distance of these galaxies and their velocity, how fast they were moving away from us. This relationship, now known as Hubble's law, states that the farther away a galaxy is, the faster it is receding. It's as if the entire universe is expanding, like a balloon being inflated, with galaxies being carried along for the ride. This discovery had enormous implications. It suggested that the universe was not static, as Einstein and most other scientists had believed. Instead, it was dynamic, ever-changing, constantly expanding. And if the universe is expanding, then it must have been smaller in the past. Extrapolate backwards far enough, and you arrive at a single point, a state of infinite density from which the entire universe originated. This, in essence, is the Big Bang theory, the prevailing cosmological model that describes the origin and evolution of the universe. Hubble's observations provided the first concrete evidence for the Big Bang. It was a revolutionary idea, one that challenged the very foundations of our understanding of the cosmos. But the evidence was compelling, and the Big Bang theory quickly gained acceptance within the scientific community. Suddenly, the universe had a history, a beginning, and perhaps an end. The prevailing question became, will the expansion go on forever, or would it eventually slow down and perhaps reverse? Now, consider this. With the universe revealed to be expanding, the natural assumption was that gravity, the universal force of attraction, would eventually slow this expansion down. It was a logical, intuitive idea. After all, gravity is constantly pulling everything together. It's what keeps our feet on the ground, what keeps the planets orbiting the sun, what holds galaxies together. So it seemed reasonable to assume that gravity would eventually win out, gradually slowing the expansion of the universe. Think of it like throwing a ball up into the air. It might start with a lot of initial momentum, but eventually gravity will slow it down, bring it to a stop, and then pull it back down to Earth. Similarly, it was believed that the initial expansion of the universe, set into motion by the Big Bang, would eventually be slowed down by the combined gravitational pull of all the matter in the cosmos. The big question was, how much matter was there? Was there enough to eventually halt the expansion and cause the universe to collapse back in on itself in a big crunch? Or was there not enough, in which case the universe would continue to expand forever, albeit at a gradually decreasing rate? The answer seemed to lie in precisely measuring the rate at which the expansion was slowing down. Astronomers geared up for an ambitious quest, a hunt for cosmic slowdown, driven by the expectation that gravity was putting the brakes on the cosmos. They were ready to measure the deceleration and finally solve the mystery of the universe's fate. Little did they know, they were about to uncover something far more surprising, something that would challenge everything they thought they knew about the universe. What if gravity wasn't winning the tug of war? What if there was something else out there, something pushing the universe apart? So, the stage was set. The theoretical framework was in place. The expectation was clear. Gravity, the relentless force that governs the motion of planets and holds galaxies together, was expected to be slowing down the expansion of the universe. The only question was, at what rate? To answer this, astronomers needed a way to measure cosmic distances with unprecedented accuracy. They needed something that could act as a cosmic yardstick, a reliable marker that would allow them to gauge the vast distances across the universe. And that's where supernovae came in. Imagine for a moment a light bulb of known wattage. If you know how bright it truly is, its intrinsic brightness, you can estimate its distance by how dim it appears. The dimmer it is, the farther away it must be. This is the basic principle behind what astronomers call standard candles, and among the brightest and most reliable standard candles in the universe are Type 1 supernovae. These aren't just any exploding stars. Type 1a supernovae are the spectacular demise of white dwarf stars in binary systems. These stellar remnants, having exhausted their nuclear fuel, siphon off matter from their companion stars. As the white dwarf accumulates mass, it eventually reaches a critical limit, a point of no return known as the Chandrasekhar limit, approximately 1.4 times the mass of our Sun. At this point, the white dwarf becomes unstable and detonates in a cataclysmic thermonuclear explosion. The beauty of Type 1. A supernovae lies in their uniformity. Because they all explode at roughly the same mass, their intrinsic brightness is remarkably consistent. This makes them incredibly valuable tools for measuring cosmic distances. They are, in essence, cosmic beacons, lighthouses shining across billions of light-years of space. Think of them as reliable mile markers on the vast cosmic highway. In the late 20th century, two independent teams of astronomers embarked on ambitious projects to measure the distances to these supernovae. These weren't small, shoestring budget operations. They were large collaborations involving dozens of scientists using some of the most powerful telescopes on Earth. The Supernova Cosmology Project, led by Saul Perlmutter and the High Z Supernova Search Team, spearheaded by Brian Schmidt and Adam Rees, were locked in a race to uncover the universe's secrets. It was a scientific competition of the highest order, driven by intellectual curiosity and the pursuit of knowledge. These teams meticulously scanned the night sky, searching for the telltale signs of these distant exploding stars. They weren't just looking for any supernova. They were specifically looking for Type 1a supernovae, the ones that could be used as standard candles. It was a painstaking process, requiring countless hours of observation and analysis. Imagine sifting through mountains of data, searching for tiny glimmers of light in the vast darkness of space. The strategy was simple, at least in theory. Find distant Type 1. A supernovae, measure their distances using their brightness, and then compare those distances to their redshifts, a measure of how much their light has been stretched by the expansion of the universe. By comparing these two quantities, distance and redshift, astronomers could determine the rate at which the universe's expansion was slowing down or decelerating. The expectation was clear. These teams were going out there to confirm what most scientists already believed to be true. They were on a hunt for cosmic slowdown, a quest to find evidence of gravity putting the brakes on the cosmos. The universe, after all, was expected to be a well-behaved, gravity-dominated system. It was a comforting, predictable picture, but the universe, as it often does, had a surprise in store. What was about to be discovered would challenge everything they thought they knew and force them to rewrite the cosmic rulebook. The universe was accelerating, but at what cost? But while these dedicated teams were meticulously hunting for cosmic slowdown, what they found instead was something truly astonishing. It was as if they had set out to prove that the Earth was flat, only to stumble upon undeniable evidence that it was, in fact, round. The whispers from those distant explosions, the faint light reaching us across billions of light-years, told a story that no one had expected. Imagine the scene. Astronomers hunched over computer screens, analyzing the data streaming in from their telescopes. They were meticulously measuring the brightness of those Type 1a supernovae, those cosmic standard candles. They knew how bright they should have been, based on their distance as calculated from their redshift. But something wasn't adding up. The supernovae were dimmer, significantly dimmer than they should have been in a universe where gravity was slowing down the expansion. It was like expecting to see a light bulb of a certain brightness at a certain distance, only to find that it was much fainter. The only logical explanation was that the light bulb was farther away than they had thought. And if those supernovae were farther away than expected, it meant that the universe had expanded more than predicted during the time it took their light to reach us. In other words, the expansion of the universe wasn't slowing down. It was speeding up. It was accelerating. The initial reaction was disbelief. Could their measurements be wrong? Were there systematic errors in their data? The teams went back over their calculations, scrutinizing every step of the process. They cross-checked their results with other observations, searching for any possible source of error. But the conclusion remained the same. The supernovae were dimmer than expected, indicating an accelerating expansion. The magnitude of this discovery cannot be overstated. It was a paradigm shift, a complete rewriting of our understanding of the universe. It was like discovering that the accelerator pedal in your car was stuck, causing you to speed up uncontrollably. But what was causing this cosmic acceleration? What was this mysterious force that was counteracting gravity and pushing the universe apart? The evidence was mounting, but it was still based on observations of a relatively small number of supernovae. Could this be some sort of fluke, a statistical anomaly? The scientists knew they needed more data to confirm their findings. They needed to look at more supernovae, spanning a wider range of distances, to be absolutely sure that the universe was truly accelerating. This marked the beginning of an intense period of observational cosmology. Astronomers around the world turned their telescopes towards the sky, searching for more of these cosmic beacons. They were racing against time, trying to piece together the puzzle of dark energy before it was too late. Before the universe expanded so much that these distant supernovae became too faint to see. The whispers from those distant explosions, once faint and uncertain, were now growing into a roar, a resounding confirmation that the universe was not behaving as we thought it should. A universe accelerating away into an unknown future, driven by a force we could not yet comprehend. What if our models of the universe were incomplete? But science, as we know, demands more than just initial hints. The supernova findings, while revolutionary, needed to withstand the crucible of scientific scrutiny. They were too important, too earth-shattering to be accepted on face value alone. So the quest to confirm the accelerating universe began, a mission that would take astronomers to the farthest reaches of the observable cosmos and push the limits of observational technology. It was a bit like a detective returning to a crime scene, not just to confirm the initial findings, but to uncover even more clues, to build an airtight case that couldn't be refuted. How do you confirm something as audacious as a universe tearing itself apart? You use every tool at your disposal. The supernova teams had used exploding stars as their cosmic markers, but scientists knew they needed independent lines of evidence, different techniques that could corroborate the initial discovery. It was about building redundancy, creating multiple paths to the same conclusion. One of the most powerful sources of confirmation came from the cosmic microwave background, or CMB. This isn't just some faint radio static. The CMB is nothing less than the afterglow of the Big Bang, the faint echo of the universe's fiery birth some 13.8 billion years ago. It's a cosmic baby picture, a snapshot of the universe when it was only 380,000 years old. The CMB is remarkably uniform, but it does contain subtle temperature fluctuations, tiny variations in heat that provide crucial information about the universe's composition, geometry, and evolution. Think of it like analyzing the ripples on the surface of a pond to understand the size and shape of the rock that caused them. By meticulously mapping these temperature fluctuations, scientists could determine the overall density of the universe and the relative proportions of its ingredients, ordinary matter, dark energy. These measurements were made by sophisticated space telescopes, like the Wilkinson Microwave Anisotropy Probe, or WMAP, and the Planck satellite, which orbited far above the Earth's atmosphere, shielded from atmospheric interference. These missions were like cosmic archaeologists, meticulously excavating the faint signals from the early universe, and what they found was stunning. The CMB data strongly supported the existence of dark energy, confirming that it makes up roughly 70% of the universe's total energy density. It was an independent validation of the supernova results, a powerful echo from the dawn of time. But the confirmation didn't stop there. Scientists also turned to large-scale galaxy surveys, ambitious projects that aimed to map the distribution of millions of galaxies across vast volumes of space. These surveys were like creating a three-dimensional map of the entire cosmos, charting the positions of galaxies and galaxy clusters like stars on a celestial map. The distribution of galaxies isn't random. They're arranged in a vast cosmic web, a network of filaments and voids shaped by gravity and the expansion of the universe. By studying the patterns in this cosmic web, scientists could learn about the influence of dark energy on the growth of cosmic structures. Dark energy, you see, inhibits the formation of large-scale structures. It counteracts gravity, making it harder for galaxies to clump together. So, by measuring the clustering of galaxies at different distances, astronomers could infer the strength of dark energy over cosmic time. These galaxy surveys, such as the Sloan Digital Sky Survey, or SDSS, provided yet another independent confirmation of accelerated expansion. They showed that the growth of cosmic structures was indeed being suppressed, just as predicted by the dark energy hypothesis. The evidence was mounting, converging from multiple directions. Supernovae, the CMB, galaxy surveys, all pointed to the same inescapable conclusion. The universe was not only expanding, but accelerating. The runaway cosmos wasn't a fluke. It was a fundamental feature of reality. It was like having multiple witnesses at the scene of a crime, all independently corroborating the same story. The case for dark energy was becoming increasingly airtight. So what are the implications for the future of the universe? The evidence was mounting, converging from multiple directions. Supernovae, the CMB, galaxy surveys, all pointed to the same inescapable conclusion. The universe was not only expanding, but accelerating. The runaway cosmos wasn't a fluke. It was a fundamental feature of reality. It was like having multiple witnesses at the scene of a crime, all independently corroborating the same story. The case for dark energy was becoming increasingly airtight. So what are the implications for the future of the universe? But let's pause for a moment and consider the human side of this scientific revolution. What happens when decades, centuries even, of established scientific thought are overturned? What happens when the very foundations of our understanding of the cosmos are shaken to their core? The answer, of course, is that history is made, and in 2011, that history was recognized in the most prestigious way possible. The Nobel Prize in Physics, that coveted gold medal that represents the pinnacle of scientific achievement, was awarded to Saul Perlmutter, Brian Schmidt, and Adam Riess. These are the lead scientists of the two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, whose groundbreaking observations revealed the accelerating expansion of the universe. The Nobel Committee recognized the profound impact of their work, acknowledging that it had fundamentally changed our understanding of the cosmos. But winning a Nobel Prize isn't just about personal glory. It's about validation, recognition from the highest levels of the scientific community that your work has had a transformative effect. It's a signal to the world that something important has been discovered, something that demands attention and further investigation. It's like a royal decree, officially declaring that the cosmic rulebook has been rewritten. And rewriting the cosmic rulebook is exactly what this discovery did. It wasn't just a minor tweak, a small correction to our existing models. It was a complete overhaul, a paradigm shift that forced scientists to rethink everything they thought they knew about the universe. It was like discovering that the laws of gravity suddenly stopped working as expected. It was a game-changer of epic proportions. Before the discovery of dark energy, our cosmological models were relatively simple. We had the Big Bang, the expanding universe, and gravity, which was expected to slow down that expansion. The universe was composed of ordinary matter, the stuff we can see and touch, and dark matter, that mysterious substance that interacts gravitationally but doesn't emit or absorb light. But with the discovery of dark energy, this neat and tidy picture was shattered. Suddenly, there was this new, dominant component, this invisible force that was pushing the universe apart. And it wasn't just a small player. Dark energy made up nearly 70% of the total energy density of the universe, dwarfing the contributions of ordinary matter and dark matter. Science had to incorporate this new reality. Cosmological models had to be revised to include dark energy, to account for its effects on the expansion of the universe and the growth of cosmic structures. It was like adding a massive new piece to a jigsaw puzzle, a piece that completely changed the overall picture. The universe was far more complex, far more mysterious than anyone had previously imagined. This wasn't just about adding a new ingredient to the cosmic recipe. It was about fundamentally changing our understanding of the universe's evolution and its ultimate fate. If dark energy continues to dominate, the universe will continue to accelerate, expanding forever into an increasingly vast and empty future. Galaxies will drift further and further apart, eventually disappearing beyond our observable horizon. The night sky, once filled with the light of countless stars, will slowly fade into an infinite, lonely darkness. Or perhaps dark energy might not be constant. Perhaps it changes over time, growing stronger or weaker, leading to even more dramatic scenarios. The possibilities are endless, and the stakes are incredibly high. The ultimate fate of the universe, and everything within it, hinges on the nature of this mysterious dark energy. So, the Nobel Prize wasn't just an award. It was a call to action. It was an acknowledgement that the discovery of cosmic acceleration had opened up a new frontier in cosmology, a frontier that demanded exploration and understanding. It was a signal to scientists around the world to focus their attention on this mysterious force, to unravel its secrets, and to determine its ultimate impact on the universe. The quest was on, and Einstein's blunder became a gift that keeps on giving, but what if it's not enough? So the Nobel Prize wasn't just an award. It was a call to action. It was an acknowledgement that the discovery of cosmic acceleration had opened up a new frontier in cosmology, a frontier that demanded exploration and understanding. It was a signal to scientists around the world to focus their attention on this mysterious force, to unravel its secrets, and to determine its ultimate impact on the universe. The quest was on, and Einstein's blunder became a gift that keeps on giving. But what if it's not enough? Let's turn our attention to a concept that could very well be the missing piece of this cosmic puzzle, a ghostly presence woven into the very fabric of space-time, the cosmological constant. Now, this isn't some modern invention cooked up to explain away dark energy. This idea has a lineage stretching back to one of the titans of physics, Albert Einstein. Remember that biggest blunder we talked about? Well, get ready for Einstein's revenge. The cosmological constant, in its simplest form, is the energy density of empty space. That's right. Even where there's nothing, there's something. Empty space, it turns out, might not be so empty after all. Quantum mechanics, the theory that governs the subatomic world, predicts that even in a perfect vacuum, particles and antiparticles are constantly popping in and out of existence, creating a seething foam of energy. It's a bit like a crowded nightclub, even when it appears relatively empty. There are always people coming and going, creating a constant buzz of activity. This vacuum energy, as it's known, could be the source of the cosmological constant, a constant energy density that permeates the entire universe, pushing everything apart. Imagine an invisible force field, subtly but relentlessly stretching space, driving the accelerated expansion we observe. It's a deceptively simple idea, elegant in its simplicity, yet profoundly disturbing in its implications. Why disturbing? Because when scientists try to calculate the value of this vacuum energy using quantum mechanics, they run into a monumental problem. The theoretical calculations predict a value that is vastly, astronomically larger than what we observe. It's not just a little bit off. It's off by a factor of 10 to the power of 120. That's 1 followed by 120 zeros. To put that into perspective, it's like trying to measure the distance from the Earth to the Sun and being off by the size of an atom. It's a discrepancy so enormous that it has been called the worst theoretical prediction in the history of physics. This is the crux of the problem. If the cosmological constant is indeed the source of dark energy, why is its value so incredibly small? Why isn't the universe flying apart at an unimaginable rate? It's a question that has plagued physicists and cosmologists for decades, and one that has no easy answer. It's the equivalent of discovering that your car engine is producing enough power to launch you into orbit, but is somehow only using enough to crawl along in first gear. One possible explanation is that there's some unknown mechanism, some subtle cancellation effect, that is suppressing the vacuum energy. Perhaps there's a hidden symmetry in the universe that we haven't yet discovered, a symmetry that cancels out most of the vacuum energy, leaving only a tiny residue. It's like a perfectly balanced seesaw, with incredibly heavy weights on both sides, carefully calibrated to remain perfectly level. Another possibility is that our understanding of quantum mechanics, or even gravity itself, is incomplete. Perhaps there are new physics beyond the standard model, new particles or forces that we haven't yet accounted for. It's like discovering that the laws of aerodynamics don't fully explain how a bumblebee flies. It forces you to rethink your fundamental assumptions. The cosmological constant, despite its simplicity, presents a profound puzzle. It fits the observational data reasonably well, suggesting a constant energy density everywhere, driving a steady acceleration. But the theoretical challenges are immense. How can empty space have energy? And why is that energy so incredibly small, yet still powerful enough to drive the expansion of the entire universe? This conundrum has led some scientists to explore alternative explanations for dark energy, ideas that challenge the very foundations of our understanding of the cosmos. What if dark energy isn't constant but something far more dynamic? So the cosmological constant, despite its elegant simplicity, leads us to an uncomfortable truth. Could it be that our understanding of the universe, as profound as it seems, is still fundamentally incomplete? Perhaps we are missing a crucial piece of the puzzle, a missing ingredient that would finally reconcile theory with observation. It's a bit like trying to assemble a complex machine with a key component missing. You might be able to get it to work, but it will never perform at its full potential. This nagging discrepancy has driven scientists to explore alternatives, to consider the possibility that dark energy might not be constant after all. What if instead of being a static background energy, dark energy is something more dynamic, something that changes over cosmic time? This is where the concept of quintessence comes into play. Think of quintessence as a kind of cosmic chameleon, a dynamic energy field that permeates space, but whose strength and properties can evolve over billions of years. Unlike the cosmological constant, which is fixed and unchanging, quintessence can change its energy density and pressure over time, potentially leading to different expansion rates at different epochs in the universe's history. It's like a cosmic dial, constantly adjusting the expansion rate of the universe. Where does this quintessence come from? Well, it's a theoretical concept, so we don't yet know for sure. But one idea is that it's associated with a new type of fundamental field, similar to the electromagnetic field or the gravitational field, but with unique properties. These fields are a part of what makes up quintessence. Imagine a vast, invisible ocean of energy, constantly flowing and shifting, influencing the behavior of the universe on the grandest scales. One of the appealing features of quintessence is that it could potentially solve the coincidence problem. Remember, that's the puzzle of why dark energy and matter have roughly the same energy density today, even though they've evolved differently over cosmic time. It seems like a cosmic coincidence that we happen to live at this particular epoch when these two components are roughly balanced. It is a concept that has cosmologists scratching their heads. Quintessence offers a possible way out of this conundrum. If dark energy is dynamic, its energy density might have tracked the energy density of matter in the past, ensuring that they remained comparable throughout cosmic history. It's like two dancers, perfectly synchronized, moving in harmony across the cosmic stage. But how would we detect quintessence? How would we distinguish it from the cosmological constant? Well, the key lies in measuring its equation of state. This is a parameter that describes the relationship between the pressure and energy density of dark energy. For the cosmological constant, the equation of state is exactly -1, a fixed value that never changes. But for quintessence, the equation of state can vary over time depending on the properties of the field. Measuring the equation of state of dark energy is a challenging task, requiring extremely precise observations of the universe's expansion history. Astronomers use a variety of techniques to do this, including supernova surveys, measurements of the cosmic microwave background, and studies of the large-scale structure of the universe. It's like trying to decipher a faint whisper in a noisy room, requiring sophisticated instruments and careful analysis. If we could detect a change in the equation of state of dark energy over time, it would be strong evidence for quintessence. It would tell us that dark energy is not just a constant background energy, but a dynamic, evolving force that is shaping the fate of the universe. Of course, quintessence is just one possible explanation for dark energy. There are other theories out there, some even more radical, that challenge our fundamental understanding of gravity itself. The universe remains enigmatic to us all. What if the accelerating expansion isn't due to dark energy at all, but to something even more profound? The quest to understand the invisible hand that is shaping reality is far from over. So we are left pondering the possibility that dark energy isn't some exotic substance lurking in the shadows, but rather a symptom of something even more profound. What if the accelerating expansion of the universe isn't due to a mysterious force at all, but to gravity itself, behaving differently on cosmic scales than Einstein's theory predicts? It's a radical idea, challenging the very foundation upon which modern cosmology is built. But as history has shown us time and again, some of the greatest scientific breakthroughs have come from questioning established dogma. Imagine for a moment that you are a seasoned detective meticulously investigating a complex crime scene. You have all the usual suspects lined up: dark energy, quintessence, perhaps even some exotic form of vacuum energy. But what if the real culprit isn't any of these? What if the crime itself, the accelerating expansion, is a result of a fundamental misunderstanding of the laws of physics? What if gravity itself is playing tricks on us? This is the essence of modified gravity theories. They propose that Einstein's theory of general relativity, while incredibly successful at describing gravity on smaller scales, like within our solar system, might break down on the vast scales of the cosmos. It's like discovering that the laws of Newtonian physics, so reliable for everyday life, don't apply at velocities approaching the speed of light. The implications of this are staggering. It means that our current understanding of gravity, one of the fundamental forces of nature, might be incomplete. It's a humbling thought, a reminder that even our most cherished theories are subject to revision in the face of new evidence. But how can we even begin to modify something as fundamental as gravity? Well, that's where things get really interesting. There are a number of different approaches, each with its own unique set of predictions and challenges. One popular class of modified gravity theories is known as F of R gravity. These theories propose that the strength of gravity isn't constant, but varies depending on the curvature of space-time. It's a bit like saying that the rules of geometry themselves change on cosmic scales. Another approach involves adding extra dimensions to space-time. This might sound like something out of science fiction, but string theory, one of the leading candidates for a theory of everything, predicts that our universe may have far more than the 3 spatial dimensions we experience. These extra dimensions, curled up at incredibly small scales, could influence the behavior of gravity on large scales, mimicking the effects of dark energy. It is like discovering a hidden room in your house that completely changes the layout of your house. Now, you might be asking, why would we even consider modifying gravity? After all, Einstein's theory has been tested and confirmed countless times. Well, the answer is simple: the accelerating expansion of the universe. If we can't explain this acceleration with our current understanding of gravity, then we have to consider the possibility that something is missing. Modified gravity theories offer a tantalizing alternative to dark energy. They attempt to explain the accelerating expansion without invoking any new energy fields or exotic substances. Instead, they propose that gravity itself is the source of the acceleration. It's like saying that the solution to the mystery has been right in front of us all along. But testing these theories is a daunting task. The effects of modified gravity are subtle, and they only become apparent on the largest scales. It's like trying to detect the faintest whisper against the backdrop of a roaring ocean. Astronomers are using a variety of techniques to test modified gravity theories. They are studying the distribution of galaxies across the universe, looking for subtle deviations from what is predicted by general relativity. They are also measuring the bending of light around massive objects, a phenomenon known as gravitational lensing, to see if it differs from Einstein's predictions. It is an attempt to use the entire universe as a giant laboratory to test the very laws of physics. These observations are pushing the limits of our technology and ingenuity. They require incredibly precise measurements and sophisticated analysis, but the potential reward is enormous. If we can confirm that gravity is indeed behaving differently on cosmic scales, it would revolutionize our understanding of the universe. It is as profound as it is groundbreaking. But even if we do find evidence for modified gravity, it doesn't necessarily mean that dark energy doesn't exist. It's possible that both dark energy and modified gravity are playing a role in the accelerating expansion of the universe. It is like solving a mystery only to discover that there were multiple people involved. The truth is, we still don't know for sure what is causing the universe to accelerate. Dark energy remains one of the biggest mysteries in modern physics. But by exploring alternative explanations like modified gravity, we are pushing the boundaries of our knowledge and getting closer to a complete understanding of the cosmos. Could our understanding of gravity be incomplete? The answer to that question may hold the key to unlocking the secrets of the universe. The universe is full of surprises, perhaps more than we thought. We've explored dark energy, wrestled with Einstein's legacy, and mapped the vast expanse of the cosmos, but a truly perplexing question lingers. It's a question that cuts to the heart of our place in the universe, a question that some cosmologists have called one of the greatest unsolved puzzles in science. Why is the density of dark energy comparable to the density of matter today? Think about it. From the Big Bang until about 8 billion years ago, matter, both the ordinary kind and the mysterious dark kind, was the dominant component of the universe. Gravity ruled the roost, slowing down the expansion and pulling things together. But then, something strange happened. Dark energy, which had been lurking in the background, began to assert its dominance. It started pushing the universe apart at an ever-increasing rate, eventually overtaking matter as the primary driver of cosmic expansion. Now, here's the rub. If dark energy is constant, as the cosmological constant suggests, or even if it changes slowly over time, its dominance today seems incredibly coincidental. It's as if we just happen to be living at the precise moment in cosmic history when dark energy and matter are roughly balanced. It is like stumbling into a room where two clocks happen to strike midnight at the exact same second, a fleeting alignment in an otherwise chaotic world. Imagine rolling a pair of dice. What are the odds that you'll roll double sixes? It's a relatively rare event, a 1 in 36 chance. But what if you rolled those dice not once, but billions and billions of times over the course of the universe's entire history? The odds of rolling double sixes at some point become almost certain. But the cosmic coincidence problem is different. It's not just about the odds of something happening at some point. It's about the odds of something happening right now, at the particular moment in cosmic history when we, as observers, happen to be around to witness it. To illustrate this, consider the analogy of a sandcastle. Imagine building a magnificent sandcastle on the beach, complete with towering turrets, intricate moats, and delicate carvings. You spend hours perfecting every detail, transforming a simple pile of sand into a work of art. But as the tide rolls in, the sandcastle is slowly eroded, its features gradually washed away. Now, what are the odds that an archaeologist arriving on the beach at some random point in the future would find your sandcastle in a state of perfect equilibrium, where the erosion is just balanced by the remaining structure? It's highly unlikely. The archaeologist would most likely find either a pristine sandcastle, untouched by the tide, or a flattened mound of sand, completely destroyed by the waves. Similarly, the cosmic coincidence problem asks why we happen to live at a time when dark energy and matter are roughly balanced, a fleeting moment in the universe's history. Why didn't we evolve much earlier when matter dominated, or much later when dark energy will have completely taken over? Some scientists have suggested that there is a deeper explanation for this coincidence, a hidden connection between dark energy and matter that we don't yet understand. Perhaps there is some unknown interaction between these two components, some subtle feedback mechanism that keeps their densities roughly comparable. It is like discovering a hidden thermostat in your house, constantly adjusting the temperature to maintain a comfortable balance. Another possibility is that the coincidence is simply a selection effect. Perhaps life can only arise in a universe where dark energy and matter are roughly balanced, and we just happen to live in such a universe. This is known as the anthropic principle, the idea that our existence places constraints on the properties of the universe. Imagine a vast multiverse, a collection of countless universes, each with different physical laws and different amounts of dark energy. In most of these universes, dark energy would be so strong that galaxies would never form, or so weak that the universe would collapse in on itself. Only in a tiny fraction of these universes, those with just the right amount of dark energy, would life be possible. And we, of course, would have to live in one of those rare, life-friendly universes. But the anthropic principle is controversial. Some scientists find it unsatisfying, arguing that it is more of a philosophical statement than a scientific explanation. It's like saying that the reason you won the lottery is because you bought a winning ticket. It's true, but it doesn't really explain anything. So, where does this leave us? The cosmic coincidence problem remains one of the most perplexing puzzles in modern cosmology. It challenges our understanding of dark energy, matter, and the very nature of the universe. Is there a deeper explanation for this coincidence, or are we just lucky observers? Perhaps the answer lies in a completely different direction, in a new theory of gravity, or a radical rethinking of our fundamental assumptions about the cosmos. Perhaps the question itself is flawed, based on a misunderstanding of the underlying physics. Whatever the answer may be, one thing is certain. The cosmic coincidence problem is a reminder that our understanding of the universe is still far from complete. It is not only about rewriting our textbooks, it is about opening our eyes to a completely different paradigm. We are still in the early stages of a grand scientific adventure, an adventure that may ultimately reveal the deepest secrets of reality. As we continue to probe the depths of the cosmos, what new mysteries await us, lurking just beyond the horizon? So we are left pondering the possibility that dark energy isn't some exotic substance lurking in the shadows, but rather a symptom of something even more profound. What if the accelerating expansion of the universe isn't due to a mysterious force at all, but to gravity itself behaving differently on cosmic scales than Einstein's theory predicts? It's a radical idea, challenging the very foundation upon which modern cosmology is built. What other secrets does the universe hold? But as we grapple with modified gravity and the cosmic coincidence, it's easy to lose sight of one of the most remarkable tools we have for understanding the universe, the cosmic microwave background, or CMB. Imagine a photograph, not of your family, not of a beautiful landscape, but of the universe itself as a newborn infant. This isn't science fiction. It's precisely what the CMB offers. This ancient light, the afterglow of the Big Bang, holds within it a treasure trove of information about the universe's earliest moments and its subsequent evolution. Think of the Big Bang as a cosmic flashbulb, igniting the universe in a burst of energy and light. As the universe expanded and cooled, this light stretched and redshifted, eventually becoming the microwave radiation that we observe today as the CMB. It's like hearing a faint echo of a distant explosion, a whisper from the very beginning of time. Now, this cosmic background radiation is incredibly uniform. If you were to look at it with your eyes, you would see a nearly perfect glow across the entire sky, a faint hum of microwave energy coming from all directions. But within this uniformity lie tiny temperature fluctuations, subtle variations in heat that are like fingerprints on the face of the early universe. These temperature differences are minute, only a few parts in 100,000, but they hold crucial clues about the universe's ingredients and its overall geometry. These fluctuations weren't just random noise. They are the seeds of all the structures we see in the universe today: galaxies, clusters of galaxies, and even the vast cosmic web all originated from these tiny density variations in the early universe. It's like planting a seed and watching it grow into a towering tree, a process shaped by the initial conditions and the surrounding environment. By studying the patterns of these temperature fluctuations, scientists can determine the universe's overall geometry, whether it's flat, curved like a sphere, or curved like a saddle. It's like using the angles of a triangle to determine the shape of the Earth, a technique that's been used for centuries. But perhaps the most remarkable thing about the CMB is that it provides independent evidence for the existence and proportion of dark energy. Remember those supernova observations and galaxy surveys? They all pointed to a universe dominated by this mysterious force. Well, the CMB tells the same story, but in a completely different way. By analyzing the size and distribution of the temperature fluctuations in the CMB, scientists can determine the universe's overall composition: how much ordinary matter, how much dark matter, and how much dark energy there is. And the results are stunning. The CMB data strongly supports the existence of dark energy, confirming that it makes up roughly 70% of the universe's total energy density. It's like having a second witness at the scene of a crime, independently corroborating the testimony of the first witness. The CMB provides powerful, independent evidence that the universe is indeed dominated by dark energy, solidifying our understanding of the cosmos. These measurements are so precise that they have allowed us to create a remarkably accurate model of the universe, a model that describes its evolution from the Big Bang to the present day. It's a triumph of modern cosmology, a testament to the power of human ingenuity and scientific inquiry. Consider for a moment the Planck satellite, a space telescope that orbited the Earth, meticulously mapping the CMB with unprecedented precision. It's like building the world's most sensitive thermometer and pointing it at the sky, measuring the faintest variations in temperature with incredible accuracy. The data from Planck has revolutionized our understanding of the early universe, providing us with a detailed picture of its composition and geometry. But the CMB isn't just about confirming what we already know. It also raises new questions and challenges our assumptions about the universe. For example, the CMB reveals some intriguing anomalies, large-scale patterns that don't quite fit with our standard cosmological model. What do these anomalies mean? Are they just statistical flukes, or do they hint at something more profound, something that challenges our fundamental understanding of the universe? It's like discovering a strange symbol in an ancient text, a symbol that defies interpretation and hints at a hidden meaning. Perhaps these anomalies are a sign that our universe is just one of many, that we live in a multiverse of countless universes, each with different physical laws and different properties. Perhaps the CMB is providing us with a glimpse into this multiverse, a tantalizing hint of the vast cosmic landscape beyond our own universe. The CMB paints a consistent picture of a dark, energy-dominated cosmos. As we continue to study this ancient light, what other secrets will it reveal? And will those secrets bring us closer to understanding the true nature of dark energy? It is like having a map that shows our current position, but what directions will lead us to unknown territory? The adventure of discovery continues. Is the universe truly a random scattering of stars and galaxies, a chaotic jumble of cosmic debris? Or is there a hidden order, a grand design etched across the heavens? What if I told you that the seemingly random distribution of galaxies is actually a vast, interconnected web, a cosmic tapestry woven by the opposing forces of gravity and dark energy? Imagine a vast ocean, not of water, but of space itself. And in this ocean, galaxies are like islands, clustered together in some areas, leaving vast voids of emptiness in others. This isn't just a poetic analogy. It's a visual representation of what astronomers call large-scale structure, the grand architecture of the universe. For billions of years, gravity, the relentless force of attraction, has been pulling matter together, drawing galaxies into dense clusters and superclusters. It's a cosmic dance, a slow and graceful ballet performed on the grandest stage imaginable, but this dance is not without its antagonist. Dark energy, that mysterious force driving the accelerated expansion of the universe, is constantly working against gravity, pushing galaxies apart, and inhibiting the formation of large-scale structures. It's like a sculptor shaping a masterpiece, with gravity meticulously carving intricate details, while dark energy subtly erodes the overall form. The resulting sculpture, the large-scale structure of the universe, is a testament to this ongoing cosmic struggle. The distribution of galaxies across the universe isn't random. It forms a vast cosmic web, a network of filaments and voids that spans billions of light years. These filaments, the dense strands of the web, are where galaxies tend to congregate, drawn together by gravity. In between these filaments lie vast voids, regions of space that are relatively empty of galaxies. Think of it like a sponge, with its intricate network of pores and solid material. The solid material represents the filaments of galaxies, while the pores represent the voids. Or perhaps a neural network, with neurons arranged in dense clusters connected by long, thin axons. The universe is in a constant battle to decide what will win gravity or dark energy. Understanding the large-scale structure of the universe is crucial for unraveling the mysteries of dark energy. By studying the patterns in the cosmic web, astronomers can infer the strength of dark energy and its influence on the growth of cosmic structures. It's like studying the ripples in a pond to understand the size and shape of the object that disturbed the water. One of the key tools for studying large-scale structure is the phenomenon known as baryon acoustic oscillations, or BAO. Now, that might sound like a mouthful, but the concept is actually quite elegant. Imagine the early universe as a hot, dense soup of particles, a primordial plasma. Within this plasma, sound waves propagated, creating ripples and oscillations in the density of matter. These sound waves eventually froze in place, leaving their imprint on the distribution of galaxies. These imprints are like cosmic yardsticks, providing a standard measure of distance that astronomers can use to map the universe. By measuring the size of these BAO features at different distances, astronomers can determine how the universe's expansion has changed over time. It's a little like finding a set of fossilized footprints that tell us how fast the creatures were moving billions of years ago. The discovery of BAO was a major breakthrough in cosmology. It provided a new and independent way to measure the expansion history of the universe and to probe the nature of dark energy. Studying galaxy clustering and BAO provides a key observational probe of dark energy's effects. It allows astronomers to measure the expansion history of the universe and to test different models of dark energy. However, our knowledge of how these structures formed is still limited, and it may take decades before a deeper understanding can be achieved. Imagine using the distribution of galaxies to test our fundamental understanding of the universe. Does dark matter interact with regular matter? How did the first galaxies form? The possibilities are truly endless. This isn't just about mapping the positions of galaxies. It's about understanding the underlying physics that governs the universe, the forces that shape the cosmos and determine our ultimate destiny. With so much knowledge to gain, the adventure has only just begun. What terrifying fate awaits our cosmos? The vast cosmic web, a testament to the tug-of-war between gravity and dark energy, stretches across billions of light years. But how do we, mere inhabitants of a small planet orbiting an ordinary star, even begin to comprehend such immensity, let alone map it with any degree of accuracy? How do we see the invisible hand shaping reality? The answer, unsurprisingly, lies in our ingenuity, our relentless pursuit of knowledge, and a whole lot of very powerful telescopes. Imagine trying to understand the Earth's oceans without ever leaving the land. You could study the tides, analyze weather patterns, and examine the creatures that wash ashore, but you'd only be scratching the surface. To truly understand the oceans, you'd need ships, submarines, and sophisticated instruments to explore its depths and chart its currents. Similarly, to unravel the mystery of dark energy, we need to venture out into the cosmos, not physically, but through the eyes of our telescopes. The quest to understand dark energy is, in many ways, a technological arms race against cosmic ignorance. It's a race to build ever more powerful telescopes and develop ever more sophisticated techniques to probe the farthest reaches of the universe. It's a battle waged not with weapons, but with mirrors, lenses, and cutting-edge sensors. Consider the Dark Energy Survey, or DES, an ambitious project that painstakingly mapped a vast swath of the southern sky. Using the Victor 4-meter Blanco telescope in Chile, DES sought to measure the distances to hundreds of millions of galaxies, searching for subtle distortions in their shapes caused by weak gravitational lensing. This effect, predicted by Einstein's theory of general relativity, is the bending of light around massive objects like galaxies and galaxy clusters. It acts like a cosmic magnifying glass, subtly warping the images of distant galaxies and providing clues about the distribution of dark matter and dark energy along the line of sight. It's like trying to understand the flow of a river by observing how it bends the light passing through it. The Dark Energy Survey scrutinized an area equivalent to 1/8 of the entire sky, observing galaxies billions of light years away. With those images and data, scientists sought to better understand dark energy's influence on the structure and expansion of the universe. But the Dark Energy Survey is just the beginning. The next generation of telescopes promises to revolutionize our understanding of the cosmos. One of the most ambitious is the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, or LSST. Scheduled to begin operations in Chile, the Rubin Observatory will survey the entire visible sky every few nights, creating a time-lapse movie of the universe. It will be able to detect faint supernovae, map the distribution of billions of galaxies, and track the movements of asteroids and other objects in our solar system. The observatory will collect images and analyze them, offering new insights in the mysterious cosmic dance. Imagine a telescope so powerful that it can capture the light from billions of galaxies, revealing the faint whispers of dark energy with unprecedented clarity. That is the Vera C. Rubin Observatory, a game-changer in the quest to understand the universe. But ground-based telescopes aren't the only players in this cosmic game. Space-based telescopes, like the European Space Agency's Euclid mission and the Nancy Grace Roman Space Telescope, offer a unique vantage point, free from the blurring effects of Earth's atmosphere. These telescopes will be able to observe the universe in wavelengths of light that are blocked by the atmosphere, providing a more complete picture of the cosmos. Euclid, for example, is designed to map the geometry of the universe and to study the evolution of cosmic structures. It will measure the shapes and distances of billions of galaxies, searching for subtle distortions caused by weak gravitational lensing and baryon acoustic oscillations. The information will help scientists determine the properties of dark matter and dark energy and address fundamental questions about the universe's origins and ultimate fate. The Nancy Grace Roman Space Telescope, named after NASA's first chief astronomer, will be even more powerful. It will feature a wide-field imager that can capture vast swaths of the sky in a single image, allowing it to map the universe much faster than previous telescopes. The Roman Space Telescope will also be equipped with a coronagraph, a device that blocks the light from bright stars, allowing it to observe faint exoplanets orbiting those stars. It is believed that in less than 1 year, the Nancy Grace Roman Space Telescope will gather more data than the Hubble Space Telescope has collected since its 1990 launch. These telescopes, both ground-based and space-based, are designed to work together, each providing a unique piece of the puzzle. They represent a coordinated assault on the mystery of dark energy, a global effort to unlock the secrets of the cosmos. And what about supernova hunting, the technique that started it all? It's still a vital part of the quest. Astronomers are constantly searching for these cosmic beacons, using sophisticated computer algorithms to sift through vast amounts of data, identifying the telltale signs of exploding stars. It's like searching for a needle in a haystack, but with the fate of the universe hanging in the balance. These new telescopes and surveys are not just about collecting data, they are about developing new techniques for analyzing that data, new ways of extracting the subtle signals of dark energy from the vast cosmic noise. It's a constant process of innovation, a never-ending quest to improve our understanding of the universe. The more data scientists collect and analyze, the closer they come to determining the true nature of dark energy. As the data pours in and technology advances, we inch ever closer to answering questions that could change everything. The universe continues to challenge us, so what other mind-bending elements await us, hidden in plain sight? The relentless march of technology and the ever-increasing precision of our observations have painted a picture of a universe in constant flux, a cosmic battleground where gravity and dark energy wage an eternal war. But what if the story doesn't end with a slow, gradual fading into oblivion? What if dark energy, instead of remaining a constant or even diminishing force, were to grow stronger over time, becoming a truly malevolent cosmic power? Could the universe be headed for a catastrophic end, a scenario so violent and destructive that it makes the Big Bang look like a gentle whisper? That terrifying possibility is known as the Big Rip, a cosmic doomsday scenario where the accelerating expansion of the universe doesn't just continue, but intensifies to the point where it overcomes all other forces, tearing apart everything in existence. Imagine a runaway train hurtling down a track, gaining speed with each passing moment, until it finally derails in a spectacular explosion of metal and fire. That, in essence, is the Big Rip. But what would cause dark energy to become so powerful? The answer lies in a theoretical concept known as phantom energy. This isn't your garden variety dark energy. This is dark energy on steroids, a hypothetical form of energy with even more bizarre properties. You see, the defining characteristic of phantom energy is that its energy density actually increases as the universe expands. It's like a cosmic snowball rolling downhill, growing larger and more destructive with each passing rotation. This is in stark contrast to ordinary matter, whose density decreases as the universe expands, spreading out and becoming more diffuse. If phantom energy were to dominate the universe, the consequences would be catastrophic. The accelerating expansion would become so intense that it would eventually overcome the gravitational forces holding together galaxy clusters. These vast collections of galaxies, the largest structures in the universe, would begin to disintegrate, their member galaxies pulled away from each other by the relentless expansion. But that's just the beginning. As the expansion continues to accelerate, the phantom energy would begin to tear apart individual galaxies, ripping apart their spiral arms and scattering their stars across the vast cosmic void. Our own Milky Way galaxy would be no exception, succumbing to the ever-increasing pull of phantom energy. The devastation wouldn't stop there. As the Big Rip approached, the phantom energy would begin to overwhelm even stronger forces, like the electromagnetic forces that hold atoms together. Stars would be torn apart, their constituent elements scattered to the winds. Planets would explode, their rocky surfaces pulverized into dust. And finally, in the last moments before the Big Rip, even atoms themselves would be ripped apart, their nuclei torn from their electrons, their fundamental particles scattered into the infinite void. The universe would be reduced to a soup of elementary particles, a sea of disconnected quarks and leptons, forever separated by the accelerating expansion. It's a truly horrifying vision, a cosmic nightmare where everything we know and love is ultimately annihilated by the relentless force of phantom energy. Some calculations suggest that if our universe is dominated by phantom energy, the Big Rip could occur in as little as 22 billion years. A blink of an eye on the cosmic timescale. Is this our ultimate fate? Is the Big Rip the inevitable destiny of the universe? The answer, thankfully, is that we don't yet know. The existence of phantom energy is still purely theoretical. We have no direct evidence that it exists, and our current observations suggest that dark energy is more likely to be a cosmological constant, a constant energy density that doesn't change over time. However, the possibility of phantom energy cannot be ruled out entirely. Our observations of dark energy are still relatively limited, and it's possible that we could detect evidence of its existence in the future. The hunt for dark energy continues, and it is an adventure that will require observation and sophisticated technology and analytics. Imagine if we could peek into the future, much like Dr. Strange did when he glanced into the 14,605 alternate futures. The potential to see how it all ends would give us a chance to prevent the Big Rip from happening in the first place. Perhaps the answer is not to prevent it, but to learn how to live with the eventual doom. Is this the ultimate fate awaiting our cosmos? Or will the universe meet a less violent, more gradual end? That is the question that drives cosmological research today and the pursuit of a greater understanding of our own universe. But what if the universe's fate isn't a dramatic tear, a cosmic explosion that wipes out everything in an instant? What if instead it's a slow, agonizing fade into nothingness? A less violent, perhaps, but infinitely more chilling prospect. Imagine a universe governed by a cosmological constant. Dark energy, in this scenario, is not some phantom force that grows stronger over time, but rather a steady, unchanging presence, forever pushing the galaxies apart. What awaits us then? A scenario often referred to as the Big Freeze, or, perhaps even more poetically, heat death. Picture this. Galaxies, once clustered together in cosmic neighborhoods, begin to drift away from each other, the vast distances between them growing ever larger. It's a slow, relentless process, a cosmic diaspora driven by the inexorable force of dark energy. Eventually, these galaxies will accelerate away from us so quickly that their light will never reach us. They will disappear beyond our observable horizon, vanishing from our view as if they never existed. Future astronomers, looking out into the night sky, might see nothing but our own Milky Way, completely unaware of the vast cosmic ocean that lies beyond. It is like being stranded on a remote island, with no hope of rescue, no contact with the outside world. The universe, once a vibrant and bustling place, will become increasingly isolated, a collection of lonely islands adrift in an endless sea of emptiness. But the isolation is not just visual. As the universe expands, the density of matter decreases. Galaxies become more and more dilute, the distances between stars growing ever larger. Eventually, the raw materials needed to form new stars will be exhausted. Star formation will cease. Think of it as a cosmic clock winding down. The universe, once a hotbed of stellar activity, will gradually cool and darken, the fires of star birth extinguished forever. Stars, like our own sun, will eventually burn through their nuclear fuel and fade away, leaving behind only faint remnants, white dwarfs, neutron stars, and black holes. Even these remnants will not last forever. Over unimaginable timescales, protons themselves, the building blocks of matter, may decay, gradually dissolving everything into elementary particles. Black holes, those cosmic vacuum cleaners, will eventually evaporate through Hawking radiation, slowly leaking away their mass until they disappear altogether. The universe will become an increasingly cold, dark, and empty place. It is a scenario of cosmic isolation and eventual entropy, the slow, inevitable march toward disorder and decay. There are no more stars, and eventually no more light. What is left is just empty space, and this darkness will eventually engulf everything that exists. Consider the words of T.S. Eliot, "This is the way the world ends, not with a bang, but with a whimper." It is a fitting description of the Big Freeze, a universe that slowly fades away, its energy dissipating into the infinite void. Is there any escape from this chilling fate? Can we somehow cheat entropy, reverse the flow of time, and rekindle the fires of creation? Or are we doomed to witness the slow, agonizing demise of the universe? Perhaps, as Stephen Hawking once mused, the greatest mystery is why we are here at all. Perhaps the true tragedy of the Big Freeze is not the loss of energy or the extinguishing of light, but the loss of possibility. The universe, once brimming with potential, will become increasingly stagnant, its future predetermined, its fate sealed. The potential for new discoveries, new creations, and new experiences will gradually diminish, until all that remains is an empty, unchanging void. Even the music of the spheres will eventually fade into a silent oblivion. However, this grim fate is not certain. It is based on our current understanding of dark energy, an understanding that is still far from complete. Perhaps, as we continue to probe the depths of the cosmos, we will discover new physics, new laws of nature that offer a way out of this seemingly inevitable destiny. For now, we can only imagine what the far future holds and continue to explore what secrets the universe holds for us to find. But what if, despite these potential cosmic apocalypses, there's something more fundamental at play? What happens when our observable universe shrinks, when the lights of distant galaxies vanish one by one? But what if, despite these potential cosmic apocalypses, there's something more fundamental at play? Something that overshadows even the grandest of cosmic finales? Imagine a slow, silent vanishing act, not of the universe itself, but of our view of the universe. A cosmic recession, not of matter, but of opportunity. What happens when our observable universe shrinks, when the lights of distant galaxies vanish one by one, not because they've exploded or faded, but because they've simply drifted beyond our reach? Regardless of whether the cosmos ends in a big rip or a big freeze, dark energy dictates a future that's undeniably, profoundly lonely. Think of it as a cosmic case of limited bandwidth. The The universe may be teeming with activity, with countless galaxies evolving and interacting, but if their signals can't reach us, it's as if they never existed at all. As dark energy continues to accelerate the expansion of space, distant galaxies are, in effect, receding from us faster and faster. Now here's the kicker. There's a point at which that recession exceeds the speed of light. It's a concept that can bend the mind, but remember, it's space that's expanding faster than light, not the galaxies themselves moving through space. What this means is that those galaxies will eventually cross a cosmic event horizon, a point of no return beyond which their light can never, ever reach us. They become causally disconnected, forever beyond our observable universe. It is like watching ships sailing into the fog, their lights disappearing, never to be seen again. Now, picture future astronomers, millennia from now. They inherit a sky vastly different from the one we see today. Many of the galaxies that currently dot our night sky will have vanished, receding beyond the cosmic horizon. Imagine inheriting an old photo album, but most of the pictures have faded or been torn out. You only have fragmented clues of a past you can never fully know. These future scientists might be completely unaware of the true scale and richness of the universe. They might conclude that the Milky Way is, in essence, the only galaxy that exists, or perhaps one of a very few. They would be missing 70%, 80%, maybe even 90% of the galaxies that were once visible. Their view of cosmic history would be radically skewed. They might underestimate the age of the universe, miscalculate its expansion rate, and develop completely inaccurate cosmological models, all because they're missing a crucial piece of the puzzle: the light from those now vanished galaxies. It is like a historian trying to piece together a lost civilization with only a handful of artifacts. This cosmic isolation isn't just a scientific problem. It's a philosophical one. It speaks to the fundamental limits of knowledge, the inherent constraints on our ability to understand the universe. Is it possible that there are aspects of reality that will forever remain beyond our grasp, not because of technological limitations, but because of the very nature of the cosmos itself? Could there be countless other galaxies, perhaps even other universes, forever beyond our ability to observe or interact with? It raises a profound question. What is the value of knowledge if it is ultimately incomplete? What does it mean to be a cosmic civilization, striving to understand the universe when the universe itself is actively concealing its secrets from us? Is it a never-ending quest to chase ever-vanishing signals from civilizations that we may never be able to see? Perhaps there's a strange beauty in this cosmic isolation. Maybe it forces us to appreciate what we can see, to cherish the knowledge we do have, and to focus our efforts on exploring the mysteries that remain within our reach. Perhaps it makes us more humble, more aware of our place in the vast, ever-expanding cosmos. The universe may be tearing itself apart, but it's also offering us a unique opportunity, a fleeting glimpse of a cosmos that will never be seen again. Will we be able to unlock its secrets before the lights go out? The challenge is clear, and what does the next generation of experiments reveal? So the universe may be tearing itself apart, but it's also offering us a unique opportunity, a fleeting glimpse of a cosmos that will never be seen again. Will we be able to unlock its secrets before the lights go out? The challenge is clear, and what does the next generation of experiments reveal? Imagine a vast, shadowy landscape, where the familiar landmarks of space and time begin to blur. The quest to understand dark energy isn't simply about peering deeper into the cosmos. It's about chasing shadows, subtle hints hidden within the faint light of distant supernovae and the intricate patterns of the cosmic microwave background. This isn't a sprint. It's a marathon, a cosmic marathon, with the fate of the universe hanging in the balance. The initial discovery of dark energy sent shockwaves through the scientific community. It was a revolutionary moment, but it also opened a Pandora's box of unanswered questions. What exactly is dark energy? Is it a constant force, a kind of cosmic background hum, or does it evolve over time, waxing and waning with the ebb and flow of the universe? And perhaps, most importantly, what does it all mean for our ultimate destiny? These are not easy questions to answer. Dark energy is elusive. It doesn't interact with light, making it impossible to observe directly. We can only infer its existence through its effects on the expansion of the universe, like trying to understand the wind by watching the leaves rustle in the trees. So how do we chase something we can't even see? The answer lies in precision cosmology, a new phase of exploration that relies on increasingly sophisticated instruments and techniques. It's a shift from simply discovering dark energy to meticulously measuring its properties, pinning down its elusive nature with ever greater accuracy. Think of it as moving from simply knowing that a ghost exists to carefully studying its every whisper, every shadow, every subtle manifestation. At the heart of this quest is the equation of state, a kind of cosmic fingerprint that describes the relationship between the pressure and energy density of dark energy. This single number, often represented by the letter W, holds the key to understanding dark energy's true nature. If W is exactly -1, as predicted by Einstein's cosmological constant, then dark energy is a static, unchanging force. But if W is different from -1, or if it changes over time, then we're dealing with something far more dynamic, something that could rewrite our understanding of the cosmos. Determining the precise value of W is a monumental challenge. It requires incredibly accurate measurements of the universe's expansion history, spanning billions of years. Astronomers are using a variety of techniques to tackle this challenge, each with its own strengths and limitations. Supernova surveys, for example, continue to play a crucial role. By meticulously measuring the distances to Type 1a supernovae, those cosmic standard candles, astronomers can chart the expansion of the universe with ever greater precision. It's like using a fleet of cosmic lighthouses to guide us through the vast darkness of space and time. But supernovae are just one piece of the puzzle. Astronomers are also turning to other techniques such as baryon acoustic oscillations, or BAO, and weak gravitational lensing to probe the nature of dark energy. These methods provide independent and complementary ways of measuring the universe's expansion history, allowing scientists to cross-check their results and reduce the risk of systematic errors. It's as if we're observing dark energy from multiple angles, each providing a unique perspective and helping us to build a more complete picture. To achieve this, the next generation of experiments will require massive data sets, sophisticated computer algorithms, and a global collaboration of scientists. One of the most ambitious of these experiments is the Dark Energy Spectroscopic Instrument, or DESI, located at the Kitt Peak National Observatory in Arizona. DESI is designed to measure the redshifts of millions of galaxies, creating a three-dimensional map of the universe with unprecedented detail. By studying the distribution of galaxies and the patterns of BAO, DESI will be able to probe the expansion history of the universe with incredible accuracy. And then there's the European Space Agency's Euclid mission, a space-based telescope designed to map the geometry of the universe and to study the evolution of cosmic structures. Euclid will measure the shapes and distances of billions of galaxies, searching for subtle distortions caused by weak gravitational lensing. Its data will provide scientists with invaluable clues on the properties of dark matter and dark energy. The Vera C. Rubin Observatory is expected to have its first light in late 2024. The observatory hopes to revolutionize our knowledge of the universe. Data collected will help scientists better understand the origins and destiny of the universe. These experiments are not just about collecting data, they are about testing fundamental theories of physics. If dark energy is indeed a cosmological constant, as predicted by Einstein, then its equation of state will remain constant over time. But if dark energy is something more dynamic, like quintessence or modified gravity, then its equation of state will evolve over cosmic history. By meticulously measuring the equation of state of dark energy, scientists hope to determine whether it is truly constant or if it evolves, narrowing down the theoretical possibilities and potentially revolutionizing our understanding of the cosmos. Perhaps it's all about finding the subtle variations, the almost imperceptible shifts in the cosmic shadows. The quest requires meticulous observation and sophisticated analysis. As scientists continue to meticulously measure the properties of dark energy, what new surprises might they uncover? What if dark energy isn't the only invisible hand shaping reality? The quest, it would seem, only intensifies. With each new telescope, with each refined measurement, the outline of dark energy sharpens, yet its substance remains frustratingly elusive. We can map its influence across the cosmos, charting the way it subtly warps the fabric of space-time, but we still can't answer the most fundamental question of all. What is it? Is it a new kind of particle, a ghostly presence that permeates the universe, interacting with matter in ways we haven't yet imagined? Or is it a more fundamental property of space itself, a kind of energy inherent in the void? The truth is, we simply don't know. And maybe that's the most exciting part of all. The universe has continually thrown us curveballs when we think we have it figured out. Think of it as exploring a vast, uncharted ocean. We've mapped the coastlines, identified the major currents, and even glimpsed some of the strange creatures lurking beneath the surface. But the deepest trenches, the most mysterious regions of the ocean, remain unexplored, beckoning us to venture further into the unknown. Dark energy may behave differently in different portions of the universe that are close to each other. Perhaps you are wondering about the specific value of dark energy. Why does it have the strength that it does? Why is it that particular number and not something vastly larger or smaller? It turns out this is one of the biggest quandaries in physics today. If the energy density of dark energy were even slightly different, the universe would look very different. Galaxies might never have formed, stars might never have ignited, and life, as we know it, might never have arisen. It's a bit like tuning a radio. If you're even slightly off frequency, you might hear static or garbled voices, but you won't hear the clear signal you're looking for. The universe seems to be finely tuned for life, and the value of dark energy is one of the key knobs that has to be set just right. And then there's the question of interaction. Does dark energy interact with dark matter, that other mysterious component that makes up the bulk of the universe's mass? Or with ordinary matter, the stuff that makes up stars, planets, and us? We know that dark energy interacts with gravity, influencing the expansion of the universe, but could it also be influencing other forces, other particles? Perhaps dark energy is causing dark matter to do something strange. Imagine the universe as a vast, intricate ecosystem where all the different components are interconnected and interdependent. Dark energy might be playing a role in this ecosystem that we haven't yet recognized, subtly influencing the behavior of dark matter, or even affecting the fundamental laws of physics. Some scientists even wonder if dark energy has some connection to dark matter. These are just some of the unanswered questions that continue to drive research in cosmology. They are questions that require a combination of theoretical insight, observational data, and technological innovation. It is a challenge, but one that scientists across the globe are continuing to challenge. It requires a global collaboration of scientists, engineers, and technicians, all working together to unravel the secrets of the universe. And yet, for all our progress, dark energy remains one of the deepest and most challenging mysteries in modern physics. It's a cosmic puzzle that has stumped some of the brightest minds on the planet. Perhaps the answer lies in a completely new theory, a revolutionary idea that will rewrite our understanding of the cosmos. Or perhaps it's hidden in plain sight, waiting to be discovered in the vast trove of data that is being collected by our telescopes. What happens when scientists uncover a new element that no one has ever heard of before? What does it do to our understanding of the origins of life? One thing is certain, the quest to understand dark energy is far from over. It's a journey that will take us to the very edge of human knowledge, challenging our assumptions and pushing the boundaries of what we think is possible. Will it lead to a scientific dead end? Or will we uncover answers that change our view of reality as we know it? We've chased the whispers of supernovae across billions of light years, peered into the infant universe with the cosmic microwave background, and wrestled with Einstein's ghost. Yet after all this, what have we truly discovered? Is dark energy just a cosmic oddity, a strange footnote in the story of the universe? Or is it something far more profound, a fundamental force that shapes reality itself? Perhaps the answer, like the force itself, is hiding in plain sight. It's easy to get lost in the equations, the mind-bending theories, and the mind-numbing distances. But let's step back for a moment and consider the bigger picture. Here's the truth, stripped bare of all the jargon. We live in a universe that is dominated by something we don't understand. Something invisible, something mysterious. Something that makes up nearly 70% of everything. Think about that for a moment. Everything that you can see, everything that you can touch, everything that you can comprehend, is just a tiny sliver of reality. We are, in essence, living in a cosmic shadow, surrounded by an unknown force that is actively shaping our destiny. This isn't just an astronomical curiosity, it's a philosophical earthquake. It challenges our most fundamental assumptions about the nature of reality. For centuries, we have believed that we could understand the universe through observation and reason, that we could unlock its secrets with the power of our minds. And yet, here we are, confronted with a force that defies our comprehension, a force that seems to be pushing the universe apart at an ever-increasing rate. Are we seeing the forest for the trees, or are we just a leaf on a tree? The discovery of dark energy has revolutionized cosmology, forcing us to rewrite our textbooks and to rethink our place in the universe. It is a humbling reminder of how much we still have to learn, how much we still don't know. Think of it as discovering that the map you've been using for your entire life is incomplete, that there are vast, uncharted territories waiting to be explored. This isn't just a scientific problem, it's a human one. It speaks to our inherent desire to understand the world around us, to make sense of the chaos, and to find meaning in the universe. And yet, the more we learn, the more we realize how little we truly know. What answers are we searching for only to discover more questions along the way? Perhaps that's the beauty of science. It's not about having all the answers. It's about the relentless pursuit of knowledge, the unwavering commitment to question everything, even our most cherished beliefs. The story of dark energy is a story of cosmic proportions, a story of a universe being torn apart by the unknown. It's a story that is still being written, and we are all, in our own way, a part of it. As dark energy shapes our future, we can only imagine where it will take us next. So what is the legacy of dark energy? What will future generations say about this moment in cosmic history? Will they look back and marvel at our ingenuity, our ability to probe the depths of the universe and to uncover its hidden secrets? Or will they shake their heads in pity, wondering why we were so blind, so unable to grasp the true nature of reality? Perhaps they will say that we were like sailors charting a course through a storm, guided only by the faintest glimmer of light, never knowing what dangers lay ahead, or that we were like archaeologists unearthing a lost city, piecing together the fragments of a forgotten civilization, never fully understanding its culture or its customs. What if the real answer to dark energy is something that is impossible for a human to ever understand? But whatever they may say, one thing is certain. The story of dark energy will continue to inspire wonder, to challenge our assumptions, and to remind us that the universe is far more mysterious and far more beautiful than we could ever imagine. With each mystery we solve, another surfaces, and the cycle will continue for eternity. The invisible hand is shaping reality, and perhaps the greatest discovery awaits us.